to the organizers, for inviting me. I really enjoyed the stay in the place and the atmosphere here in Santa Barbara. So let me introduce first my collaborators on this work, on this first part of the talk, which are Manuel Gessner, which was a postdoc in Florence and now is in Spain, and Valentin Gebert, that is completing his postdoc position in Florence. And with Luca, we are both working in this place. This is near the institute. This is a hill of Arcetri. And nearby here, there is a house where Galileo Galilei lived the last year of his life. No? He was reclused outside the Florence walls, and the beautiful villa. And if you come, you can visit it. In the basement, actually, there was a place where a huge amount of barrels of wine, where it's not clear how Galileo managed to all these barrels of wine. So apparently he had a lot of parties with friends coming visiting. So he was, outside Florence, excluded by Florence, but apparently we were kind of smooth with him. Anyway, so I would like to talk about a problem that actually has not been, I want to introduce and discuss with you a problem that has not been investigated quite in the literature, okay? And, but I think we deserve much more attention in the sensing metrological community, because it's quite tricky, but fascinating. So let me tell you briefly. So I'm going to talk about a single parameter estimation. So for instance, the phase, the magazine, the interferometer, and you want to estimate the phase from the results of the measurement, which I'm going to call X here. So you need an estimator, which means that you collect the results of your measurement, you replace your function, which defines the estimator. So in this case, the probability that given a value of theta, you generated some results. So you replace the numbers x1, xm, you repeat m times the measurement. You replace this here, and you found the maximum, this maximum light estimator, which is, the best we have in the market so far, okay, as estimator. And we know that if a number of measurement, the statistics is pretty big, this saturates the Cramer-Rao lower bound, which is one of a number of measurement, one of the efficient information defined here. Asymptotically, in a number of measurements. So we see that if we plot here the variance multiplied by the number of measurement versus a number of measurements, this is the region where we, both experimentalists and theorists, like to live, okay? It's a comfortable zone where everything is nice and smooth. Why? Well, because here we have this magic theorem called central limit, which tells that whatever your probabilities are eventually become Gaussians, which is quite beautiful actually, and once you become Gaussian, you have large signal to noise ratio, everything is asymptotic and biased. It's beautiful, okay? But now, if you have a small signal to noise signals, or your statistics not big enough, or your probability are not Gaussian, something bad happens. So typically people in this field draw a line here, which is not really a sharp line, of course, which is called threshold, and there is a below threshold region where things become much more complicated, okay? First of all, maximum likelihood does not work, become biased, which means that you can use it and you get a completely wrong result, for instance. And the Cramer-Rao itself is still a bound, but you don't know if it can be saturated, if it can be, what you don't know anything about here. So this is actually the problem I want to discuss with you, and that's why it's also a very important problem, because there are many applications that, for instance, whenever you have a weak signal, or time varying signal, so that you cannot have time to collect statistics, okay? So you are in this region most of the time. Or, for instance, there are several problems in diagnostic when you don't want to be invasive. You want to do in vivo diagnostic. So you have to send probes to see how the cells behave or are healthy or not, but you don't want to kill the cells. So you have to send, very small number of photons, not so energetic. And so there are a lot of applications. And typically, whenever this situation, whenever people have to deal with this region here, they use a Bayesian approach. Okay? Very good. In contrast, I say Bayesian, in contrast to all this business area, which is frequentist. Now, people use Bayesian approach, but I should tell you that the Bayesian is not so innocent as you may expect. Okay? Let me tell you briefly, sorry if I just go abroad, but so let me give you this analogy, which is, I think is quite close. So you know that there are hot debates about the ontological status of quantum mechanics, right? So there are big families of interpretations which can be grouped in epistemic interpretation, realistic interpretation. So in the realistic part, there is a Bohm, many-world interpretation, epistemic, Copenhagen, and so on, which essentially are divided by what we believe is the meaning of the wave function, if there's a reality, and so on. Now, you'll be surprised to know that we don't agree on the meaning of quantum mechanics, but we don't agree on what probability is.
It's the same root of the sorry.
No, in fact. But we overlook about probability, which is something that we use every day, every time, unconsciously, or make decisions, or to bet, or whatever we want to do, and we don't think much about this. But we have a kind of the same problem in probability theory, and there actually, there are big families of interpretation, but two separate big families. We can say one is that probability is physical. It's objective, you can measure it, and so it's physical, and you measure it through the frequentist, you measure frequencies and go into a large number of measurements and so on and so forth. And there is another class, another family of interpretation, which go back to Jeffrey and Definetti in particular. We say probability just lives in our mind. It's a subjective interpretation, okay? It's not something that exists outside the world, but it's actually as a measure of what we know, of our ignorance, of our prejudice, okay? Of how much money I will bet for a specific event to occur, okay? So it's a definition for Bayesian interpretation of probability. And so whenever we use Bayesian approach in this region here, it's quite clear that this is what we are doing and what we are using. How this works in practice? Well, use your bias inversion rule. So the probability given the data, so you have some evidences, these are the results you're measuring, and given the evidences or the data, you want to calculate the probability that the true value, the phase shift, of which horse will win a race, is distributed. Distribution is probability. And to calculate this probability, you use the Bayesian inversion rule. So this is equal to a normalization constant. This is the prior, which is what you know or what you guess about the true value of the phase shift. So initially, when no experiment has been done, you assume flat, complete ignorance, okay? Then this is the likelihood, so probability that given theta as some value, this will be the results of the measurement. So you replace the results of your measurement here, and this becomes the updated information that you have in your system, updated after you replace a first measurement. So this becomes the new prior, you go back, keep going, and eventually what happens? Again, it happens nicely, smoothly, that for large number of measurements, the Bayesian uncertainties will slowly saturate and converge to the maximum likelihood and saturate the Cramer-Rao. Okay? So you remember there was a nice talk by Peter Zoller a couple of days ago, where discussing this kind of aspects. And so they converge, this von Mises theorem. So, and people typically don't bother much because we live here. People don't bother much about use of Bayesian or frequencies interdependently, regardless of the fact that there are completely different meanings. But what happens here? Whenever you have some threshold, Bayesian can be quite wild. Actually, this is kind of an example. Bayesian can be above, Bayesian mean-square fluctuation can be above the Cramer-Rao, can even be below. So it can apparently violate the Cramer-Rao theorem, okay? I say apparently because you're not supposed to compare the Bayesian variances with the frequencies, which are completely different meaning. And so, really, this region here, we can use Bayesian as most the people do whenever this has become, you're in this region. But what about frequentist bounds? So, that's the problem I want to discuss, okay? I want to calculate the frequentist bounds in this pre-threshold regime and see how these are different from Bayesian. I don't want to elaborate on the physical or the meaning of Bayesian compared to frequency. I'm just going to focus on the calculation, on what kind of instrument we have to calculate the frequentist bounds whenever you are outside the central limit. Okay? So this is the problem that I want to discuss with you. And since I like to make my life more difficult, I will also consider another aspect. So again, I consider a phase estimation, but now you can imagine that the allowed value of the phases are not a continuous, so you don't consider a problem where the phases are from 0 and pi, for instance, but they can take only a discrete set of values. This is, of course, it's a kind of generalization. You can go to the continuous limit whenever the number of phases goes to infinity, but most of the time we consider the case where phases can only pick discrete specific values, and the unknown value of the phase is just one of this ensemble. Okay? Very good. And if you ask what we know about this, outside the Bayesian approach, this is exactly what we know. And yeah, what happens in this case? Why this makes the problem more difficult? Because, the Cramer-Rao is not even defined. The Fisher formation is not even defined. Why? Because you cannot derive probabilities. There are no probabilities are discontinuous. You cannot define a derivative probability. So Fisher formation does not exist. Cramer-Rao does not exist. So here, really, we cannot even rely on the Cramer-Rao theory. Okay, so this is what I want to talk about.
And that's simply because you can't take a derivative with respect to the parameter theta.
Yes.
It's discrete and not continuous.
Right, exactly. You cannot, the derivatives do not exist because you have a discrete set of phases, including the true value is one of this, but you cannot derive. Okay, so goal. So in this scenario of discrete phases, I want to find the best unbiased estimator and calculate its variance. So unbiased means that I define an estimator, a frequentist estimator. I want to be sure that if I calculate the average of this estimator, or probability weighted by x given theta I, this will give you theta I, and not give you a completely different value. So this should be 0. So this is the definition of unbiased estimator. And then I want to calculate with this unbiased estimator its variance, okay? Which is exactly the quantity here. I want to do this without imposing any limit on the number of measurements. So I can go to infinity, or I can go to one measurement, okay? So I want to be really on the broad, on the most general situation. So this problem actually was addressed by Barankin a couple of years after the Cramer-Rao paper appeared in 49. Okay, so he wrote this paper, which actually went mostly unnoticed for various reasons. One of those is that it's a highly mathematically complicated for the typical mean-square physicist, at least, and difficult to read. And so it actually, besides a few enthusiasts, went unnoticed. There was a kind of revival of interest in the 70s in the engineering community because they want to use this approach to track. There was a specific problem they were interested in, is the tracking of the airplane and the radar. So planes are moving the radar, the signals are weak, and so on and so forth. But then again faded away the interest till today. And the solution that proposed by Barankin, he found this locally unbiased estimator at the variance. Okay, so I'm going to tell you a little bit more how this business works. So let's consider the estimator. So in this case of discrete phases. So he wrote the estimators in this form here. So this K is one phase that you choose among the set that you know are the possible values of the phases, okay? You choose it either because you know more or less what the phase is, or you choose at random. These are the ratio, the probability calculated for two different values of the phases. And these are some parameters which are derived by imposing the unbiased condition over all set of phases. Okay, so you have to solve this matrix equation. You know that theta I, theta k is for all I and k. You have to solve this equation for AI. So this can be done formally. It's just how to invert a matrix. Okay, and lambda, the phase differences, is defined somewhere in my mind. And this is the Barankin matrix. Okay, so Barankin matrix is the analog or the Fisher matrix. At the same structure is 1 over P on the true value, and the Fisher matrix are the derivative of the probabilities on the true value of the phase, but here actually there is just the product of two probabilities for different value of the phases, okay? And lambda, lambda is here. Yeah, I was looking somewhere else. And lambda is the difference between two value of the phases. So how it works? It works that you do an experiment, you don't know the value of the phase shift, and you get some x. You replace x here, okay? And you get your theta est. And then you know that this theta est is unbiased. So if you repeat the experiment many times, you calculate the average, this points to the right value, okay? This is by construction. And what about the variance? The variance is given by this quantity here. So the variance of this estimator would be larger or equal to the Barankin variance given by this expression. You can saturate, and this comes the tricky point, you could saturate this variance only if this number, this phase that you chose, is exactly the true value. So if you by chance choose the true value, you saturate sensitivity. If you got something else, you put a random value, you know that the variance will be bounded by this quantity. And this is the Barankin matrix, or Barankin information in your problem. Okay?
Can I ask a question now?
Yeah.
Right, so there's contradiction between two things you said. Number one, you want to have finite number of measurements.
Yeah.
But to construct this estimator, you said you do many measurements. And
no,
then...
I didn't say that, sorry. I say that if you do many measurements, you will find out, you can test that the estimator is unbiased.
But
that's what I
not
say.
Exactly unbiased, right?
No, it's exactly unbiased, even with a single measurement.
The problem in classical statistics, why this doesn't get more attention, is that we know that for a finite number of samples, for a lot of problems, unbiased estimation doesn't exist, or it doesn't make sense very often. So,
right. All the Barankin theory is built to say, let me elaborate on this, okay? Since you're there. So this estimator is unbiased. When I mean unbiased, I mean that satisfy this condition here, which is unbiased condition. But this is the estimator weighted with the probability for some value of the phase shift. But the estimator can be calculated even with a single measurement. So when you think about unbiased, it means that you do a measurement, you estimate your phase. This phase is not the same as the true value because it's fluctuating. It's a random parameter. But unbiased means that if you take all these values that you could get, the average of them converge to the right point. So this means unbiased. So you can prove, it's actually quite easy to prove that this is unbiased. For instance, you multiply by p dx, sorry if I go more technical, but if you multiply this by pxj, so pj, you calculate the average, this gives you theta k, and this becomes ai, pj, pi, pk, which is this term, which is theta j into theta k cancel. When you replace, you get theta j. Sorry.
Does it rely on you knowing the true parameter?
Right. It does rely in the sense that, that's the point that I was going to make, in the sense that if you don't know the true parameter, you can try to guess the best value, but you know that whatever you put here will have a variance which is large or equal to this quantity here. That's the theorem.
So the lower bound assumes that you know the true parameter.
The lower bound is
for...
saturated only if you, by any reason, you put here the true value.
Right. But
so you know that it's saturable, the lower bound, that if you use another point, the variance is large.
But I'm saying that in practice, if an unbiased estimator doesn't exist to begin with, what's the point of bounding the error?
Okay, listen, I'm going to give an example here, okay? So I'm going to convince you.
And let's hold the rest of the talks or the questions until after the talk is done. Just let him get through his slides.
Sorry?
Proceed. I'm not going to let anyone else interrupt you for the rest of your
told
talk.
me to proceed. Okay, so there are many ways to derive this quantity, to steer here. A recent one is by using a cost function. So use Lagrange multipliers to minimize the cost function, which is essentially the variance here and the unbiased condition. So you write your Lagrange equation, you minimize the problem, and you get these equations here. Okay, example. So this is an example. I admit there are not many examples which can be analytically solvable in the literature. One of these is here. So as an example, I consider the probability, this is a Poisson process. So this is the probability that if you don't have any events, this is a probability of not having any events, and this is, given this term here, you have n events. Sorry, I'm playing with words here, but essentially this is the theta that you want to estimate, and this is a number of events, okay? So by measuring number of events in your experiments, you want to estimate this parameter here. Lambda is the average of the Poisson process, and so everything is quite clear. So everything can be done analytically in this case. You can calculate the estimator, the Barankin bound, the Cramer-Rao lower bound, the maximum likelihood, bias, can calculate everything. Okay, so this is a case where it can be solved for any value of measurement m. And these are the results. Two examples. So when the true value of E2 minus lambda is equal to 0, 1, and I'm plotting here what? The Cramer-Rao. So this is a continuous variable, okay? Which I normalize to 1 here, so it's a green line. And then there is the Bayesian, which are the dots, okay? The maximum likelihood estimator is a yellow line, and Barankin is a blue line. So there are many, a few comments here actually, not many, because, for instance, let's compare, let's see maximum likelihood. Maximum likelihood does not saturate the Cramer-Rao unless you go to large M. So asymptotically converge to Cramer-Rao. But for a smaller number of measurements, you see there is discrepancies here. If you calculate the bias, you see that actually you don't get anything out of maximum likelihood. The Bayesian here are many points which fluctuates, okay? It can be above, or for other parameter, it can be even below the Cramer-Rao. And you see this huge difference, well, huge, there's a significant difference between the Bayesian approach and the exact result given by Barankin theory. So the blue line is the Barankin theory, okay? The Barankin prediction. So this is the variation, excuse me, the variance multiplied by the number of measurements given by a Barankin, okay? So this is the exact result. And so this shows how this theory works and what happens when you are outside the central limit. Eventually, your variances are can be larger, significantly larger, than the Cramer-Rao, essentially. This is the general trend that you have. Okay? So your uncertainties increases. Okay, so let me go to another aspect of this theory. So I hope that more or less I gave you a hint how this works. So another aspect which I found quite interesting is the following. So in the Barankin bound, actually, now I'm going to see the algebraic property of this bound, is relies on the inversion of the Barankin matrix, so this matrix here, okay? So this is theta, the true value of the phase, and these are all possible values of the phases. So I'm going again to the discrete phase case. For phases can belong to a set of a finite number. So this Barankin matrix actually is a sum of dyadic matrices. What it means? If you consider this term here, this element here is a product of two scalars. Okay, so this matrix here has rank 1, and then you have the sum of rank 1 matrices. So the rank of this matrix actually is bounded by the number of measurements. So what is important to emphasize here, X is the number of possible outputs or the number of measurements that you do in your system. So go 1 to capital M. And so there are two parameters here. One is the rank of the matrix, number of output, and one is dimension of the matrix. Dimension is D times D. D is the number of phases. So the dimension of this matrix actually is D over D. And if the number of output is smaller than the number of phases, the matrix cannot be inverted, and then you cannot have a bound. So there are situations where the Barankin bound diverges, okay? Does not give you any results. And this happens whenever the number of measurements in your experiment is smaller than the number of possible value of phases that you want to estimate. Okay, let me give you some practical example of how this works. So some consequences. So for instance, suppose that you have your Mach-Zehnder interferometer with n particles. In outputs, you have that, you have 10 particles, you can have 10 and 0, 9 and 1, and so on and so forth. So you have n plus 1 outputs. So this number of output introduces a scale, a natural length in your problem. It tells you that you cannot, how to say, resolve, thank you, resolve phases which are smaller than, okay, if you have an interval 2 pi, smaller than 1 over the number of outputs, m, okay? That's what I said before. Number of output is the total number of particles, essentially. So this is the minimum phase that you can resolve your interferometric experiment, okay? And the reason how this happens is because the number of outputs should be the same as the number of phases, no, discrete phases that you want to consider, and this essentially gives you this the smallest. You might interpret this as the bias that you have, the minimum bias that you have in your estimation, okay, the minimum phase you can resolve, or the minimum bias whenever you have a finite number of outputs. Same things happens if you, for instance, you do many measurements which are independent. So you consider just one interferometer, one particle, you repeat the experiment many times, and again you have a number of measurements here, which is the same scale as the number of particles. Again, in this kind of problems that you repeat the experiment many times, you introduce the same kind of. Well, maybe somebody will say, well, but this looks like a Heisenberg scaling. Okay, it is not, in the sense that this is purely classical. I'm not putting quantum mechanics in. Quantum mechanics satisfy this, of course, but I'm not relying on quantum mechanics. This just comes from the general structure of parameter estimation theory. Okay, and maybe I did not mention this, but this is the best you can do. Barankin is the best, most complete. There's some reason for that. Estimation theory that you can think of. What about if you have n qubits? Well, in this case, the number of measurements goes as 2 to the n, right? Where n is the number of qubits. And this introduces a minimum phase that you can resolve that scale as 1 over 2 to the n. And now, maybe this rings a bell, because those who are familiar with the phase estimation algorithm, which is a building block for the Shor algorithm or other algorithm in quantum computation, they know that, it will know that the limited resolution or the digit sensitivity or precision, sorry, in phase estimation problem also scale as 2 the n. Okay, the two things are related. This is the kind of ultimate bound in resolution, either in phase or in the digits, you know, that you have in your phase estimation problem. And quantum mechanics actually, in that algorithm, saturate this fundamental bound. So this is quite nice. I found this quite nice because it's very general and based on essentially no assumptions. Another example now. This is a phase estimation with a single spin, single qubits. And I consider the case, just pedagogical, where the phases, the allowed phases can have just 3 values, or 5, or 7, with the true value is pi over 2. Okay, so I consider a discrete set of possible values of phases. And now, and this is in terms of number of measurements. Okay, and so you see that this forbidden region that essentially comes from the fact that if you have, for instance, 3 phases, and you have to estimate, or you have to know where the phase, the true value is, but you know that this value is one of these 3, okay, possible values. So you need at least 2 measurements in order to start to say something meaningful about the true value of the phase shift. If you have 5 phases, then there is a larger forbidden region. You need at least 4 measurements. And this is because the number of measurements that you need to have to invert the matrix and then to have a solution for your problem should be of the order of the number of phases that you have in your problem. Okay? And this keep going. And then, well, keep going. Maybe it just have a flex here around the Cramer-Rao, and then goes down below the Cramer-Rao, which is not a surprise because you have a discrete set of values, and it goes down actually faster than 1 over m. So faster than you know how the shot noise. Oh, really? But I got questions, so maybe I do. Yeah. Okay. And it goes faster than 1 over, the variance goes faster to 0 than 1 over m. And the reason is the following. This is not a continuous phase estimation, it's discrete phase. So the probability, while you accumulate statistics, shrink. But once the probability shrink enough to distinguish between the different values of phases, so the phases are like here and here, but your probability has a width which is smaller than the distance between the phases, the system immediately collapses to the right value. Okay, very quickly. Now, I like to make connection with loosely, connection with other point, because when you do machine learning, for instance, we did this with Luca, we published some work on this, and you have the problem of training machine learning. Okay, you train your machine. And how you train the machine? Well, you have introduced a cost function. Then you have a grid of phases in your machine. So you choose some phases, and then you put results, output results, and minimize the cost function for each value of these phases that belong to the grid. And what we've observed, and now we have the analytic expression, is that if the number of if the number of measurements used in the training is smaller than the number of grids points, okay, you can get something out of a machine, but it's completely meaningless. And that's what we found out. It's impossible to train properly a machine if you have a grid of points. It can be very thin. We want to estimate theta from 0 to 2 pi. You put 10 to the 10 numbers, for instance, there. Well, if you want to train properly, you have to put at least 10 to the 10 data to train your machine, at least. Then there are other problems. Like if you do too much, sorry, where I am. If you want to do too much, you overtrain the machine, there are other problems. But I also want to mention that if you want to train in the Barankin way your machine, then the cost function, you have to use the cost function that I used before to derive the equations. Okay, I will go quickly on this by introducing you a Barankin-like estimator, which is slightly different. Instead of, I change my estimator condition. I know this will come a little bit technical, but I want to make contact with Cramer-Rao. So as an unbiased condition now, I just say that the average value of your estimator with respect to the value of the phase is equal to 1. So in Cramer-Rao, you have this unbiased condition for the true value only. Here I impose this unbiased condition for all the value of the phases that belong to the set. You do exactly the same. You do your phase estimate, you calculate your variance, and this depends on the inverse of the Fisher matrix. Well, I pause just a second for you to appreciate that this is exactly the Fisher matrix that is used in the multi-parameter estimation that Luca was discussing before, with the only difference that in the multi-parameter case, there are here all the values of the phases that you want to estimate. Here, the phases are just one interferometer, and these are the probabilities for different phases of the same interferometer. But the mathematics and is exactly the same. So there is a kind of connection between the multi-parameter and this phase estimation business. Okay, that example was essentially the same, but I skip it. And then I would say that if you are bored, you want to find your own family of bounds, you can play, because this is quite general. You impose your unbiased condition, and you can derive your favorite bound. But let me tell you, in the literature, there are two families of bounds, okay? So one where the probability are differentiable with respect to the phase, and one where the probability are not, because they are discretely distributed. To the first family belongs the Cramer-Rao, the standard Cramer-Rao that I just introduced, the Bhattacharya, which I not discussed, but this contains a higher order of derivative calculating the true value. And when you cannot calculate derivatives of the probability, then there is the Barankin or other bounds. Why these are interesting? Because Cramer-Rao is a lower bound for all of them, okay? The best one are the Barankin for the discrete case and the extended Cramer-Rao for the continuous phase case. And out of these bounds, here, you can now start and look for approximation that can be useful. For instance, Cramer-Rao, we know that we can approximate the bound with some error propagation formula, using a moment expansion. You can do exactly the same here. You can generalize your propagation error by using one of your favorite bounds here, okay? And this can become much simpler to manage, to use in practical life, of course. And then the last question comes, of course, these are all classical, I discussed, how you can get the quantum version of them. So as Fisher information can get the quantum Fisher, can we do the same here? Yes. We can get the quantum bounds. So you can you have your Barankin bounds, or one of those bounds, and you look at the minimum of this variance for all possible POVM. It's exactly a definition of quantum Fisher information. You have the Fisher information, you look for all possible measurements you can think of, and look for the best one, which minimizes this variance. And this can be solved, this problem, for the family of bounds that I've just considered. Quantum Fisher we all know, and then for the Barankin, this expression here, quantum Fisher, where these are the logarithmic derivative, if you want to call it, but which provides the matrix, the quantum matrix that enter in your bound. There are strong analogies with quantum Fisher, formal analogies, of course. And then you can introduce your quantum metrological information. which is the inverse of this quantity here, which play the same role of the quantum Fisher, okay? Has some nice properties, a convex in the density matrix, but not additive, okay? It defines a Riemann metric, which is contractive and positive and representing operations, and so on and so forth, and is strictly bounded by the quantum Fisher information. Stop talking. For pure state, okay, I'll stop talking now. For pure state, this is all these bounds collapse to the quantum Fisher. For pure state, a unit revolution. So I want to finish with this, okay, if I am allowed. There are practical applications, but I like also fundamental problems. So it was, besides metrological applications, there are different aspects that you can investigate in this framework. For instance, what has introduced statistical distance means that if you have a probability which is parameterized and changed as a function of some parameter t, you want to know how many states are distinguishable along the path. So this probability is a cloud of uncertainty. So in order to have another probability, this distance between these two should be larger than the cloud of uncertainties. And this is what defined in the limit of a larger number of measurements using the Cramer-Rao bound. Larger number of measurements because in that limit you can start with a bound. But now we can define this statistical distance for any number of measurements, even with a single measurement, because we can calculate the distance along this path by using the Barankin bound or any the best bound that I discussed before. In this case, this introduces a statistical distance, okay, given even for a single measurement, which for pure state, a unit revolution becomes one of the variance of the generator for the transformation. Okay, so I think I'll stop here. I have other slides, but I'll keep it blank, okay? Because you asked me so. Thank you very much for your attention.
Thank you. All right, very interesting talk. It's good to have a few minutes for questions and conversation. So let's begin. Who would like to ask something? All right, let's start with Klaus.
Thank you for a fantastic talk. This is really exciting. Have you looked into if it's possible to iterate? You can do two measurements to distinguish three hypotheses. Then you can alternate or add in more hypotheses and go on, or change the density around the most likely one.
Yeah, we thought about doing this, but this is kind of recent work done. I've not explored many of the implications. Actually, maybe I should say this. Most of it is not published yet. So thank you for taking notes and publish your paper on this, but please, I'm not talking, of course, I'm just kidding. But yeah, there are many directions we want to explore. One is about machine learning, application of this. One about discrimination of state, can be important for tomography, so on. So there are many aspects. And in this talk, I just want to, to show that there is this area which actually has not been explored. It can be nice and fun to explore.
Yeah, I was also excited by your talk, and I wanted to ask about this question about the incompatibility if the number of measurements wasn't greater than the number of possibilities. You say basically you have to punt and not give any estimation until you get big enough.
Yeah.
But in the sense, in the spirit of being underdetermined, you could try to think about some kind of least squares fit. And so you would do not an inverse, but like a pseudo-inverse. If you thought about doing like a pseudo-inverse to be able to get some kind of cruder estimation in this under-constraint limit.
Okay, I see that also
Lorenzo is nodding, so I'm on the right path there. Good.
So the way I understand this is the following. It's very rough. So you have D phases. I want to discriminate the phase with distinguishable outputs. That's if I want to discriminate the phases, somehow my output should also be distinguishable. You have a bunch of outputs which are devoted to this phase, a different bunch of outputs devoted to this and this and this. So if I want to discriminate D phases, at least I have D distinguishable outputs that address all the phases. So this is my naive.
But maybe discuss afterwards.
At this point, as you say, maybe I need to.
Yeah, I think you can do more,
Yeah.
but let's talk about
Very
it
good.
afterwards.
Very good.
I think, wait. There's chatter. Who's chattering?
Huh?
Okay, Lorenzo's chattering. Okay, here we go. Talk to the microphone.
No, I was just picking up on what you said and said that there are regularizers for in dynamical system theory. It's a known problem to tame invertibility and make it like quasi-invertible or pseudo-invertible with appropriate semi-norms or so.
I think this will be exciting
Yeah,
to look
so-
at it then.
But there are many things
Yeah.
very exciting. I'm just signing because I'm absorbing. So.
Yeah, me too. Okay, other questions? I think over here we had a question.
Asked sort of already by Andrew, I guess. So I can restate your no-go theorem as saying if there are fewer measurements than variables, you can't do anything, right? So this has nothing to do with statistics, Barankin, anyone, right? Is that correct?
I think this is comes out from this Barankin theory, not only Barankin, but comes out is algebraic property of this matrix.
Yeah, no, I understand that it comes out of that, but I'm saying if the statement that if you have fewer measurements than variables, then the estimation procedure is meaningless. That has nothing, I mean, that is just matrix inversion, right?
Yes, this metric inversion that tells you that, but maybe there are other arguments which brings to the same conclusion.
No, one argument and the simplest one is adequate for me.
Okay. So, but yeah, so the answer is yes. Is yes.
Okay, other questions? So I was intrigued because, you know, I've been working in this field a long time, and very often we deal with these continuous parameters, but I find it fascinating there hasn't been more work on this, say, this set of problems saying, no, it's not anything, it could be either A, B, C, or D, and you've got to choose which one it is. So it's I think it's a very natural kind of problem. I'm just surprised there hasn't been more work in this area. Maybe you can comment on the fact that this seems to have been forgotten about for several centuries.
You know, this approach here was forgotten because, actually, believe me, it's tricky. It was really difficult to get something meaningful. And also because it's heavily required numerics. So until the 80s, I mean, there are few analytical results on this. And the people struggle a little bit to deal with it, but then they give up. So I think now with machine learning and computer, this situation can change a little bit. So I think it's just historical, because Cramer-Rao is much easier.
It's easier.
You know, all the nice properties, which I love. I've been working many years on that. And this is much more, believe me, tricky. For instance, the fact that this cannot be inverted and this gives you an infinite bounds, I mean, really confused the community, because they were trying to use this bound to tracking stuff, and then everything exploded. And then at some point, they give up, which is a good reason to give up, I guess.
Yeah, I just want to iterate my same feeling. That's the same feeling what you had, like how come that this issue have been overlooked. That's how I felt when I also noticed that standard estimators, if you put noise, they go wrong. In fact, I immediately emailed Augusto, am I ignoring a lot of the literature? And I do think that also with noise, the issue of biases and invertibility, they will become more prominent, and not only for multiplicative stuff, for more complicated things. So there is commonality.
Thank you.
Okay, any other thoughts or questions? Oh yes, here we go.
Hi, thanks for a great talk. So usually when you have a discrete set of values, so people think about it as hypothesis testing. And then there are like optimal protocols for and optimal estimators in case of hypothesis testing. Is it the same? And also you showed optimization over POVM. So for multi-hypothesis testing in quantum, so we know what is the optimal P of M. Is it the same? Like the P of M that optimizes the minimal error probability, is it the same as the one that?
As I said, I've not explored all the connection because this is quite different from the usual language and approaches they use on discrimination or the problem that you're talking. So it must be a connection there. Okay, it has to be worked out. It has to be to work it out. Okay?
That's exactly right. If you say my options are A, B, C, or D, I think about these as different hypotheses
Yes.
That I have to discriminate between. So I think it's a very natural question and a good point.
Right.
Yeah.
Absolutely.
All right. If there are no more other questions, let's thank Augusto again for a great talk.
Thank you.